So in the ground state of the atoms, the orbitals are filled in order of their increasing energies. Few key points you need to include. In the ground state, the orbitals are filled, means electrons in the orbitals are filled in order of their increasing energies. And this is the way you can find out how the electrons will be filled. So it means you have to write 1s, 2s, 2p. Why? Because 1 will not have p, 2 will have p, 3 will have s, p, d, 4 will have s, p, d, f, like this. And then you will draw the oblique lines to get the sequence in which the electrons will be filled in these orbitals. Okay.
I think 5G will also be there.
Yes. So, but we won't need, normally questions won't appear. Okay. Then next is Pauli's exclusion principle. Pauli's exclusion principle is, and why the name is exclusion, because if one arrangement of four quantum number, don't read it what is written. You will understand when I explain. Okay. First, understand what I am saying. If I consider one set of four quantum numbers, I have n, l, ml, ms, and I consider any possible set of these numbers, okay, combinations. For example, I consider in fourth shell p orbital, there will be -1 0 +1. Say I consider only +1. So p subshell, this is p orbital, one of the three p orbitals, and I consider one electron only. So this is one set of all four numbers. So what Pauli said, that if for one electron, this is the possible combination of all four quantum numbers, then no other electron can have this configuration. Means there can be only one electron with one unique configuration. No two are possible. Even if these three are same, for example, the two will be differentiated by plus half and minus half. Even if these are same, this will be different. Now read the definition. No two electrons in an atom can have the same set of four quantum numbers. Why exclusion name? Exclusion name is that if one electron has this configuration will be excluded from further consideration. This cannot be considered for any other electron. So that's why the name exclusion principle. This can also be stated as only two electrons may exist in the same orbital and these electrons must have opposite spin. So even if they are in same orbital, their spin will be different. Next is Hund's rule of maximum multiplicity. Again, easy rule, but important rule. When I said that in subshell, there are orbitals. So suppose I am talking about p subshell. In p subshell, there will be three orbitals. Hund's rule of maximum multiplicity says that when the electrons start filling up in these orbitals, the pairing of electron does not take place unless all orbitals are half filled. So for example, if one electron comes here, then second electron will not be here. Second electron will go to next orbital. Third electron will go to next orbital. Now each orbital has one electron. After that, pairing will start. So this rule deals with filling up of electrons into orbitals belonging to the same subshell. Same subshell I am considering here, p subshell. That is the orbitals of equal energy called degenerate orbitals. And this rule says that pairing of electrons in any subshell does not take place until all orbitals are half filled. So first, all orbitals will be half filled. After that, fourth electron will get into px. Fifth electron will get into py. Sixth electron in pz. Then pairing will start.
Sir,
Yes.
no, sir, I got it, sir. Thank you, sir.
So it says pairing of electrons in the orbitals belonging to the same subshell does not take place until each orbital belonging to that subshell has got one electron each. That is, it is a singly occupied or half filled. Why is it so? It is because energy of the orbitals depends on the number of electrons into it. And I will be shortly talking about the symmetry, why it leads to stability. You can understand it in general way that if you have a balance, for example, okay, you have a weighing balance, okay, and in this universe, everything tries to be symmetric. For example, if you have a container of like this and you pour water at this end, the water will, if it can flow, so water can flow, it will try to achieve the same level, means symmetrical height. So if it is possible, every object in this universe tries to have symmetrical shape or symmetrical distribution. Distribution has to be symmetrical if it is possible. So in this case, suppose I have something here, it will get imbalanced like this. To balance it, first I'll have to one here also. After that, I can have second here, then again it will imbalance. So the fourth one will balance it. Similar to that one is Hund's rule of maximum multiplicity in chemistry. That first electron will come here. Now energy of this orbital will change and it will be different from these two. So the next electron, if next electron comes here, it will rather increase the difference in energy. But system will try to equate the energies of orbitals. Hence, the next electron will go to next orbital, the third electron to the next orbital. Now they are symmetric, means their energies are equal. After that, yes, electrons can get paired up. This is Hund's rule of maximum multiplicity. If it is d orbital will have, d subshell will have 5 orbitals. In this case, the electrons first will get into all 5 single electrons in all 5 orbitals, and then pairing will take place. The number of orbitals 2l plus 1. For p, l is 1. So 2 into 1 plus 1, that is 3. For d, l is 2. So 2 into 2 plus 1, 4 plus 1, 5. For f, d is 3. So 2 into 3, 2l plus 1, that is 7. So here 1, 2, 3, 4, 5, 6, 7. Next is electronic configuration. Electronic configuration is just a way to represent the distribution of electrons. Whatever we have talked about, for example, Above principle, Pauli's principle, and Hund's principle. When we combine, specifically the Above principle and Hund's rule of maximum multiplicity, that is actually electronic configuration of atoms. So suppose I say, and this is represented as like this. How many electrons are there? A, B, C are number of electrons in s orbital, number of electrons in p orbital, number of electrons in d orbital. This is the notation. So this is, suppose I say that s orbital, p orbital, d orbital like this. And I say write the electronic configuration of say magnesium. For magnesium, the atomic number is 12. And for 12, according to our principle, you need to write the electronic configuration till you cover the 12th electron. After that, you won't move further. You will move till you cover the 12th electron. So to start with 1s, so you will write 1s2 because s can hold two electrons only. In s subshell, only one s orbital, maximum two electrons. After that, you have 2s. You will write 2. So we have covered 4 electrons till now. After that, you will have 2p, but p can have 6 electrons. It's still 10 electrons for you. Then 3s2. Now I have covered 12 electrons. 2 plus 2, 4 plus 6, 10 plus 2, 12. It means the configuration, electronic configuration of magnesium will be this
2
one.
comma 8 comma 2.
Come again?
2 comma 8 comma 2. So because in 2s and 2p the electrons get added up and the rest 2 there to each.
Yes,
In
electronic
1s.
configuration, what we have studied till now, that is 2 comma 8 comma 2, right?
Yes, sir.
Which
Yes, sir.
is which is
Yes, sir.
which is you know
So
true
this is a
from here also.
representation of
If
Gauss
you see,
principle.
this is as per Above principle. Okay. So in first shell, you have only s. How many electrons are there? 2. These
Yes,
both
sir.
are of second shell. 2s, 2p. Both in
Subshell.
second shell. How many electrons? 8.
Yes.
8,
Then in third, how many electrons?
2
2.
again.
So 2 comma 8 comma 2. But this is how actually they are distributed inside the atom
Yes, sir.
within the orbitals. So we will have same logic 2 comma 8 comma 8 comma 18 comma 18 comma 32 comma 32. That will be valid here also. But how these are distributed amongst the subshell and orbitals, that is obtained by Above principle, along with Hund's rule of maximum multiplicity. So if we talk about lithium, lithium will have 3 atomic numbers, so it will be 1s2, 2s1. Why? Because it has only 3 electrons. So in 2s, we can't write 2. If we see the above principle, lithium has 3 electrons. So we will write 1s2, 2 electrons covered, then 2s, but we will not write 2s2 because that will be 4 electrons. We will write only 1 here. Then suppose we write for beryllium. Beryllium has 4 electrons. For that, it will be 1s2, 2s2. It means the last electron in lithium will be in s, will have clockwise spin. Last electron in beryllium will again be in 2s, but that will have anti-clockwise spin. That is the difference only.
First electron, first remainder among the remainders of first electron is conventionally taken as anti-clockwise.
Well, it in few guides it is different, but if I consider the NCRT clockwise and anti-clockwise,
Okay, sir.
Sir,
yes,
sir, can we determine the valency of an atom with this off-bow configuration?
yes, we can.
But sir,
Mm.
somewhere in many where the S shell is completely filled. So sir, how can we determine of that? So like in magnesium, the 3s2 cell is completely filled. So how do
Mm.
we get to know that its valency is 2?
We will compare it with the electronic configuration of noble gases to get the valence.
Okay, sir.
So beryllium will have 1s2, 2s2 in second shell also. Okay. Now boron has 5 electrons. So after 2s2, it will be only 1 electron in p. So it will be 2p1. 1s2, 2s2, 2p1. With practice, you will remember that what is the sequence 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. Okay, so 4s2 will come first, 3d will come after that. Similarly, for carbon, 6 electrons. So you will have total 2 plus 2 plus 2, 6 electrons. But as I said, above principle plus Hund's rule of maximum multiplicity we need to apply. So the last electron will not be here, rather it will go to next orbital. Until all are singly occupied, pairing will not take place. Nitrogen, 7 electrons. In oxygen, now pairing will take place in oxygen. Here, the next electron will pair in the first p orbit. After that, here, after that, here pairing will take place.
8 electrons are there in
Yes.
oxygen.
Oxygen has 8, fluorine has 9, neon has 10. Now you can see that neon is noble gas. So it will have the complete shell filled up, not only the subshell. In beryllium, if you see, okay, you have only the subshell filled up, 2s. In beryllium, this is only 2s filled up, 2p is empty. But in noble gas configuration, the subshells as well as whole shell is filled. So in second shell, there will be only 2s and 2p subshells. Both subshells are completely filled. Because all subshells are completely filled, that's why this represents noble gas configuration. Next, this topic is, slightly, as I said, what applies in universe applies in chemistry also. So this topic is related to that. And it leads to the explanation of few exceptions in electronic configuration. Whatever we have talked about electronic configuration as per the above principle here, normally this is the rule. Whatever arrows we have shown, normally this is the rule, but there are few exceptions, and those exceptions are explained by these conventions here, what I'm going to talk about. Stability of completely filled and half filled subshells. What was found that if a subshell is half filled like this or completely filled like this, these were comparatively more stable than other configurations. Comparatively more stable than other configuration. And the reason was very much what we have talked about. Symmetry leads to stability. If it is symmetric, it will try to retain that. If it is not symmetric, it will try to attain symmetry. But if it is symmetric, it will try to maintain that. So because these configurations are symmetric, both, these are more stable. The rule applies in chemistry also. So first is, when you see the electronic configurations where you have half filled and fully filled subshells, you will consider those subshells or those configurations more stable. More stable means less reactive. Less reactive. And this actually explains the exception in case of chromium and copper. What are those exceptions? First, understand those exceptions. If I say chromium, chromium has atomic number 24. And if I write its configuration, okay, as per Aufbau rule, the configuration will be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4, 10, 10, 4, 24. This should be the configuration. I hope you have written the above diagram there, whatever diagram I had shown, so that you can compare. If not, then somewhere write it, or you need to have in front of you if you have NCRT. This is the diagram I follow when I write the electronic configuration. Write it down quickly if you haven't done so, or if you don't have the diagram. So I have come up to here, 4s2 and 3d4. 1s2, 2s2, 2p2, 2p6, 3s2, 3p6, 4s2, 3d4, up to here. This is as per above principle. It should be like this. But because the half filled and fully filled orbitals are more stable, and I gave you an example that if you pour some water, it will try to equate its level if it can. Now what happens? This outer electronic configuration is represented by normally by last two orbitals. Okay? Last two orbitals. In few cases, last three, and we will talk about that when we consider that. And 4 electrons here will be.
So please show the diagram once again.
Okay, just a second. At least
So we need to draw it in 3D.
Yeah. So after 4s2, 3d4. Yeah. After 4s2.
Sir, till which number would you sir suggest to memorize this table till 3D?
No, I said that at least up to 5th here level, you need to first remember. After that, obviously, you need to go up to here, 7s.
Yes, sir.
Okay, but at least to start with till 5s, memorize it.
Okay, sir.
So 2 electrons in S and 4 electrons as per Hund's rule of maximum multiplicity, singly occupied. But what happens, because half filled configuration is more stable, 1 electron from S moves to D. Now it can happen, as I said, that if possible, only then it will happen. It can happen only if the energies of orbitals are not too different. Means they are close to each other. And in 4s and 3d, the energies are actually very close. In reality, the energies are very close. So whatever energy is here, the same, almost same energy is here. So these are called degenerate orbitals. In such cases, movement of electron from one orbital of one shell, another shell, is possible to other orbital of other shell. Now, if I consider this case, this explains the actual configuration of chromium. So chromium configuration is not this one. Chromium configuration is rather, here you have 1s2, 2s2, 2p6, 3s2, 3p6. Here you have 4s1, 3d5. This is actual configuration. Of chromium. This is theoretical configuration.
Sir, can you please explain, sir, the orbitals that you have shown here, sir? So like there's a single box, then there's 5 other boxes. Sir, can you explain that part, sir?
Come again, I couldn't understand your question.
Sir, in this, sir, you have made one square box and another rectangular box with some 5 boxes in it. So,
Because
sir, the first represents S.
s orbital has just
Yes, two
s
electrons.
subshell has only one orbital.
Yes,
D
sir.
subshell has 5 orbitals, so that's why 1, 2, 3, 4, 5 orbitals.
Sir, so one pending box of d orbital takes one electron from the s orbital.
Yes, from s orbital. So that's why this arrow there.
Okay.
Okay, this arrow I have drawn just because to explain that one electron moves from here to here. Only one electron. Now what happens? Now, if I consider this case, s orbital and d orbitals, 5d orbitals, still I have these orbitals, but s has one and d has now 5 electrons. And you can see that both are half filled. This is also half filled, so it has not lost the stability because half filled and fully filled subshells are more stable. So S in any case, whether it has one electron or two electrons, is stable. Because if it has one electron, it is half filled. If it has two electrons, it is fully filled. But this one has now attained stability because it is half filled now, this subshell. So the configuration, outer electronic configuration of chromium is different from theoretical value. And how it is explained? It is explained on the basis of the greater stability of subshells having half filled or fully filled configuration. Clear? Any confusion? Let me know. Similarly, the configuration of, before I move forward, similarly, the configuration of copper also. In case of copper, copper has atomic number 29. And as per above principle, it will be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9. First 3, 10. Next 3, 10. This is good way to remember, to count. Okay? First 3, 10. Next 3, 10. And then here you have 9 means total 29. Again the same thing. S subshell will have one orbital with 2 electrons. D subshell will have 5 orbitals with 9 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9. Now you see this one has just one electron. These 4 have 2 electrons. These 4 orbitals have 2 electrons. However, the last one has only one electron. Again, the same thing happens because these orbitals have almost same energies. One electron from here moves to this orbital. Now modified configuration is you have only one electron here because one electron moved, and in D now you have all electrons in pairs, means fully filled. In case of chromium, D subshell was half filled, one electron each in each orbital. Here it is fully filled, more stable. Similar thing happens here. So the configuration in case of copper, the actual configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d10. 1 electron in S, 10 electrons in D to attain higher stability. Exceptions, you will certainly get questions from here. Either chromium or copper, the questions based on these. This is just concept. Questions will be of different types. Same concept will be used to explain the answer. Certainly, there will be one question in your examination from here. The symmetrical distribution of electrons leads to stability. This is something we have talked about. Then related to this one is exchange of energy. These two are interrelated. Whether I am talking about symmetrical or I am talking about exchange of energy, exchange of energy is possible only if these are degenerate. And transfer of electrons is possible only if these are degenerate. So the underlying reason is same for both phenomena I am talking about. Exchange energy, the stabilizing effect arises, means increases, whenever two or more electrons with the same spin are present in the degenerate orbitals of a subshell. What it says, these electrons tend to exchange their positions, and the energy released due to this exchange is called exchange energy. The number of exchanges that can take place is maximum when the subshell is either half filled or completely filled. As a result, the exchange energy is maximum and so the stability. As I said, these are interrelated. So don't think I am talking about some different concept. No, I am talking about the same concept, but in terms of exchange of energy. Understand it diagrammatically, what I am saying. Suppose I have one electron each in each subshell, each orbital of d subshell. If I consider this electron, only this electron, okay, this can exchange itself with second, means this can go into here and this can go here. Because these have same energy, the energy difference is very, very low. So these can interchange their positions. So if I consider this one, the first can interchange with 1, it can get interchanged with 2 or 3. Okay, so 4 transitions are possible with 2, with 3, with 4, with 5. 4 exchanges by 1 electron are possible. And whenever there is any exchange, there is some work done. And during that work done, some energy will, it means is wasted. If some energy is wasted, the energy of the system will be lower than the earlier one. What I am saying, suppose the energy is 10 units and these electrons exchanged their positions because the difference in energy is very low. So exchange in the position can be just due to vibrations also. In this case, the energy is so low, it can be due to vibrations also. But when they exchange their positions, some work has to be done to exchange their positions. For example, if you move from one room to another room, you have to do some work. It means you lose some energy. So if their energy is lost, the total energy goes down. And in previous class, we talked about that if energy is low, means stability is higher. I give you an example of water. Cold water is stable. Boiling water is not stable because we have provided energy to it. That is the thumb rule throughout the universe. So if energy goes down due to these transition, atom becomes more stable. And when it can happen? It can happen when all orbitals are singly occupied. It cannot happen if orbitals are doubly occupied because there is no free space. Okay. Although it can happen if in case of copper, for example, I talked about. Here in this case, it can happen because this is empty and all the electrons have close to each other energy, degenerate orbitals. That's why the electron got transferred from S to D. So if it is possible to transfer of electron and here you have one empty position, then transitions can take place. Okay, electron can come here, this electron can go here, transitions can take place. And when transitions can take place, the energy will be lost, system will be more stable. So this is the idea to explain why these type of systems are more stable. Having said that, not too complicated questions will appear from here. This is just one statement you have to remember, rather two, that what is the reason for stability of half-filled and fully filled orbitals or subshells. You will give answer on the basis of 2 points. The first is symmetry leads to stability. Second one is this one, that exchange of electrons leads to loss of energy and atom becomes more stable. These 2 points in 2 lines you have to write. However, this point can be asked to elaborate. Okay, so you can elaborate that symmetry leads to stability. Okay? And then you can give example of half filled and fully filled orbital. Nothing more than that. Any question here? So what we have discussed, the thumb rule throughout the universe, that symmetry leads to stability. And the second one, which is related to that one, exchange of energy leads to stability. Higher the exchanges, higher the loss of energy, higher the stability. I am repeating this one because this one students don't write all the steps. I am saying the steps you have to remember. I am saying greater number of exchanges, okay, that is transfer of electrons, means higher loss of energy, means lower energy of the atom, means greater stability of that. That's all
Can
what you
you
need to
please
remember.
show the previous slide, sir? I had to just note one point to elaborate. So for the symmetry.
One more point what you can mention in case of symmetry is shielding.
Sir, how would shielding take place, sir, if even if the electrons get sub-distributed, sir, symmetrically?
Okay, understand
would-
it like this. I am considering the both configurations of copper. Okay, to explain it. Here you have s electrons, 2s electrons, and 9 d electrons. The d subshell is much larger than s, even if the d is in third shell. Understand it? P orbital, for example, in second shell will be of this much shape, for example. Then in third shell, it will be of larger size. In fourth shell, it will be even larger size because it will correspond to the shell number. But the s orbital, for example, in second will be of this size. In third will be of this size. In fourth will be of this size. Next. Now you can see that 4s is actually smaller than 3D. So in 4s, the electrons will be closer to nucleus. This is the region where electrons can be in 4s. So either electron can be here, electron can be here. So this much will be the distance of electron from nucleus. However, in case of 3D, the distance from the nucleus can be this much, which is larger. So what happens?
One has the best stability.
Come again.
Which one has the highest stability?
Yes, that's what I'm explaining now.
Okay.
So what happens here in this case? The electron, and I am drawing this one because both are concentric. The center, this center is same in all cases. Yeah, I think I erased it probably. So I'm drawing it again. The 3p orbital and so this is say 3p orbital, this is 4s orbital, and 3d orbital will be even larger than this one, but 3d I'm drawing it like this. Okay, say 3d. Yes. Switch off your mic. So here electron can be at this much distance. Here electron maximum can be at this much distance. Now what I am doing, I am drawing this S, 4s here. Because nucleus is same in the atom. Everything is concentric. This is 4s and this is 3d. D will have 4 lobes, so that's why D. Now what happens if 2 electrons are here in 4s, 2 electrons are here. These electrons can be here. And the 3d electron, say 3d electron is here. This one is 3d. Now these two 4s electrons will shield this electron. Did you get that? We talked about shielding effect.
Yes,
These
sir.
will block the force of attraction by nucleus.
Yes, sir. It will make it weaker. So for the outermost.
So these
Yes.
two electrons will actually reduce the force of attraction by nucleus to the 3d electron. So it is called shielding effect. If we have only one 4s electron, not two, then shielding effect will decrease. One electron will have less shielding effect. And that's what we are discussing here. Shielding of one another is relatively small because now that electron has moved to D. So I'm going back to explain that again. So earlier in one orbital, D orbital, there was only one, two were here. Two electrons were in 4s and one electron only was in 3D, one of the 3D. Okay. Yeah. Now what happens? This electron from here moved to D, 3D. It will not shield 3D. It is in the 3D only. So it will not shield the 3D electrons. Okay. There will be only one electron which will be shielding now the 3D orbitals. Is that clear or not? Earlier, two electrons were shielding the outer electrons. Now only one electron has shielding effect. So shielding effect has reduced. Okay. Now going back to here to explain it. Now because shielding effect has reduced, the force of attraction will increase.
Yes, so
Force of
there will.
attraction will be increased. More strongly attracted electrons means stability will increase.
Yes, sir. Okay.
Okay. So less shielding, greater force of attraction, greater stability. Exchange of energy, you need to remember these 4 points. Greater the number of exchanges, higher the loss of energy, lower energy of the system, greater stability of the atom. These are the just exchanges shown. How many exchanges are possible in each case? Greater, just this is to explain, greater the number of exchanges, greater the loss of energy, nothing else. Now the questions, and questions are most important part in this chapter. If you do the theory part, you don't focus on questions, you are not going to get marks in this chapter. Very simply put forward like that. Write the electronic configuration of elements of atomic number 10, 17, 25, 29, 37. So 10, if you remember, 1s2, 2s2, 2p6, we will stop here because we have covered 10 electrons. 2 plus 2, 4 plus 6, 10. So that will be the configuration. Then 17, 1s2, 2s2, 2p6, 3s2, 3p, 5, 10, 7. First 3 will give you 10, then you have 2 plus 5. Here you will write only 5, not 6, because you have only 17 electrons, not 18. This will be the configuration. 25, start writing as per above principle. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Remember, up to here we have 20. So you can memorize. Up to here you will always have 20. After that you have 5, and after that you have 3D. You will write only 5. Now this one, in contrast to 24, remember in 24 we had written 4s1 3d5. It is already stable, this one. It has 3d5 configuration, so it will be very stable configuration. Why? Because it has half filled configuration. This will not be very stable because it does not have half filled or fully filled configuration. This configuration will be, P will have 3 orbitals and 5 electrons will be 1, 2, 3, 4, 5 like this. This is neither half filled nor fully filled, not very stable. Okay. This will be very stable. Why very stable? Because it has completely filled 1, 2, 3, 4, 5, 6. And completely filled S also. So whole shell is completely filled, and you know 10 is of neon. That's why it is noble gas configuration. Noble gas configuration will have all the orbitals of a subshell completely filled. Okay. So some questions will be there. Few questions will ask, out of these configurations, which configurations represent noble gas configuration? So you will see those ones where all the orbitals of the valence shell are fully filled. So valence shell in this case is 2, and all orbitals S and P completely filled. So this is noble gas configuration. Then 29. 29 we have done, it is an exception. It is copper. Exception.
Sir, in the 17th one, sir, where you have written 3p5, sir, it is not very stable. Sir, but is it possible that it could take, sir, one electron from 3s2?
No.
Then,
In this case, these are not degenerate orbitals. The energies are different. That is possible only
yes,
where
sir,
the
indeed.
orbitals are degenerate.
Yes, sir, yes.
So here it will be 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d10. Instead of 4s2, 3d9, it will be 4s1 3d10 so that it attains stability. Then similarly for 37, you will write as per above principle. Okay, 4p will be there. You if you go here, okay, after 4s you have 3d and 4p is there. So we'll use 4p and 5s after that. So for 37, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 10, 10, 20. Okay. Then 3d10, 30, 10, 10, 10. Now you have 7 only. So it will be 4p6 and 5s1, 37. Good. So you need to remember above principle, at least till 5s to start with, and after that you can move further. Is the concept clear that you have to simply count the number of electrons? You need to write as per above principle and you will stop when you finish the number of electrons. There are few exceptions you have to keep in mind. Now there is another way to write this one, that sometimes if this part is very large, then you replace some part by noble gas configuration. Okay. So for example, 18 electrons you will replace by argon. 36 electrons you will replace by krypton. This is the atomic number of argon, 18. So 18 electrons are there. In krypton, there are 36 electrons. So for example, in this case, I had written as 37, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s1. So this 10, 10, 10, and 6. This is 36 configuration is of krypton. So you can write this as krypton configuration and then the remaining part 5s. So this is also a way, and this will only be, you will be able to do this only if you remember the configuration. So with practice, you will remember that configuration till here is argon configuration. Configuration till here is krypton configuration. 18, 36. Then you will be able to write quickly. Initially, you will face problem because you don't know, but with practice, it will be fine. Arjun, your question is? It is a good practice sometimes, Arjun, to mention. But if the question is simply, I have shown it just to explain so that you can understand that sometimes it will be required. But if it is not written, you don't need to write like this. The configuration is fine if you write like this or you write like this. Okay? This is something I have written just to explain that as per Hund's rule of maximum multiplicity, 2 electrons will be here, 2 electrons will be here, 1 electron will be in PC. But if you write it, it is good, not mandatory. Next question. How many unpaired electrons are present in the ground state of phosphorus? So you will write the configuration as per above principle and you will consider Hund's rule of maximum multiplicity also. So 15 will be 1s2, 2s2, 2p6, 3s2, 3p3. 10 plus 5, 15. Now, if you write 3p3, the outer electronic configuration, this is fully filled, no unpaired electron because this one will have configuration this. But 3p3 will be as per Hund's rule of maximum multiplicity, 1 electron here, 1 here, 1 here. Means 3 unpaired electrons are there. And that is the question. How many unpaired electrons are present? So answer will be 3. Now these type of questions are very important and usually these will appear in your examination. These are simple ones. The first one, very simple. And why the ionic form is important? Because the rule is slightly different. For iron 26, first you will always write the configuration of atomic form. I am repeating it. Don't write the configuration of iron directly. Because if you consider it ionic form, Fe2 plus means it has lost 2 electrons. Fe2 plus, it gained +2 charge after losing 2 electrons. So it has normally 26 electrons, 2 lost 24. So you can write configuration of 24. And few students who think that 24 is exception, they might write the configuration of chromium, which is not true. Okay. And why it is not true? That is something you need to understand. I'm explaining it. So first rule is, even when it is in ionic form, first write configuration of neutral atomic form only. Don't consider iron. So first you will write configuration of iron. That will be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6, 10, 10, 6, 26. Now understand the rule. When electrons are lost, it is not reverse of above principle. Filling up of electrons is as per above principle. Reverse is not true. Removal of electron will not be reverse of above principle. The electrons will always be removed from outermost shell. For cations, electrons are always removed from outermost shell. Write it somewhere. It means the electrons will not be removed from here because reverse is not true. Rather, electrons will get removed from here. So the configuration of Fe2 plus will be 1s2, 2s2, 2p6, 3s2, 3p6, 3d6. And these type of questions normally will be there. Ionic form configuration, because your teachers know few students will make mistake here. The rule is very simple. For cations, electrons are always removed from outermost shell. Reverse of above principle does not exist. Next is chlorine. That is chloride ion here. So write the structure of chlorine first. Chlorine 17 structure. 1s2, 2s2, 2p6, 3s2, 3p5, 10 plus 7, 17. But Cl minus will have 18 electrons. So now it will be as per above principle. Filling up of electrons is as per above principle. So it will be 1s2, 2s2, 2p6, 3s2, 3p6. Because Cl minus means there are 18 electrons. And Cl minus 18 electrons means configuration of argon. Argon has fully filled cap. Any confusion till now, you need to ask. Next, give the symbol of the atom whose ground state corresponds to the configuration. So you just need to count the electrons. 10 electrons, neon.
10 argon.
10, 8, 18 argon.
18 electrons.
Yes. Write the electronic configuration of following ions. Hydrogen has 1 electron, H minus will have 2 electrons, means it will be 1s2. Hydrogen would have had 1s1, but this minus means one more electron, so 1s2. Na plus, sodium has 11 electrons, plus means it has lost 1 electron, 10 electrons, 1s2, 2s2, 2p6, 10 electrons.
Sir, is there any separate rule for anions, sir, in terms of gaining electrons, sir?
No. There are few exception type things which I will be talking about. Okay. But the different type of rule is for cation, not for anion. O2 minus means it has gained 2
Are the
electrons.
same as Na plus.
Yeah. Oxygen has 8, it has gained 10.
1s2, 2s2, 2p6.
For sodium, if I'm not considering this, for sodium it would have been 3s1. But because it will lose 1 electron after
Sir,
Yes,
yes,
sir.
sir. Sir, it will
3s1
maintain
start, so
electrons.
3s1 is the outermost shell. So electron will go from outermost shell, this will disappear.
It will be removed.
Yeah. The rule is same. F
Sir, it
minus.
is necessary to show.
No, not necessary. You just need to write the configuration.
Okay, sir.
That is for explanation. Chlorine has 9 electrons plus 1, again 10. Same configuration, 1s2, 2s2, 2p6, 10. Yellow light emitted from a sodium lamp has a wavelength of 580 nanometers. Wavelength is 580 into 10 to the power minus 9 meters is given. Nu is equal to C by lambda. Whenever we are talking about light, light contains photon and photons move with the speed of light 3 into 10 power 8 meters. So substitute the values and get the answer. 3 into 10 to the power 8 meters divided by 580 into 10 power minus 9 meters. And wave number will be just 1 divided by lambda.
Lambda.
Simple question. Next, find energy of each of the photons which correspond to light of frequency. This. So first case, frequency is given 3 into 10 to the power 15 hertz and energy is required and energy is h nu, that is 6.626 into 10 to the power minus 34 joules second into nu 3 into 10 to the power 15 hertz per second. Multiply, get the answer. Have a wavelength of this much. So second one, wavelength is given 0.50 into 10 to the power minus 10 meters. Is in angstrom. I converted it to meters. And then energy is hc by lambda. Substitute the values 626 into 10 to the power minus 34 multiplied by 3 into 10 to the power 8 divided by 0.50 into 10 to the power minus 10. You will get energy in joules. Next, calculate the wavelength, frequency, and wave number of a light whose period is given.
Sir, is it frequency?
So if period is given, you can calculate frequency, right?
Yes.
So once you get frequency,
1 by T.
yes, 1 by T. So once you get frequency, you can use it to get the wavelength and wave number.
Yeah.
Because wavelength will be C by nu. Nu is equal to C by lambda. Lambda will be C divided by nu. C is 3 into 10 power 8 to get the answer. And wave number will be 1 by lambda. Get the answer. Next, what is the number of photons of light with a wavelength of 4000 picometer that provide 1 joule of energy? So total energy is 1 joule. And you know 1 photon energy is h nu. Total energy is n h nu.
It's new.
So total energy is given 1 joule. And you have to calculate h is 6.626 into 10 to the power minus 34. And wavelength is given, so nu you need to calculate as C by lambda. Okay. So here you can write hc by lambda. So C is 3 into 10 to the power 8 and divided by lambda 4000 into 10 to the power minus 12 because it is in picometer. 1 picometer is 10 to the power minus 12 meter. Substitute the value and you get the answer.
Sir, you had given us this question in the assignment as well. All these
Mhm.
questions.
Come again?
Sir, given us all these questions in the assignment. Sir, assignment 1 and
Yes, yes.
we
These are
taken
the
at the
assignment. And after 1 month or 2 months, I will be asking you to solve these questions again and submit before your
Yes.
examination. A photon of wavelength, just let me see the time whether we have that much time or not. Just last question. A photon of wavelength is given lambda 4 into 10 to the power minus 7 meter. It strikes on metal surface. The work function of the metal being W naught is 2.13 electron volt. Calculate the energy of the
Let's have
photon.
1.6, no, sir, for work function.
Come again?
Sir,
What are-
for work function, sir, so if we have to convert it, sir, then we divide it by 1.6.
Yes, we have to. Yes. So if you need to convert it into joules, you need to multiply it by 1.6 into 10 power minus 19. joules.
Okay, sir. And sir, to convert to work function, we have to divide, sir, by 1.6.
Work function is given in electron volt. So you have to convert it into joules. Otherwise, you will not be able to use it with SI units.
Yes, sir.
Okay. So first convert it to joules and then we will use it. So here it is first energy. Okay. So photon wavelength is given, energy will be, if you say W or E, let it be E naught. That will be Hc by lambda. So substitute this lambda here, you will get the energy. And E naught is given. Here energy you will get in joules. Kinetic energy of the emission, once you have got E, apply E equals to E naught plus kinetic energy.
C naught gives us.
So E comes from here, E naught comes here, from here, kinetic energy, you can calculate. Next, velocity of the photoelectron. Once you have got kinetic energy, you apply the formula kinetic energy equals to half mv square, you get the velocity from here.
Sir, for M, we will use the electron mass, no, sir? 9.1.
Yes, it is electron here, you will use photoelectron.
Yes, sir.